Here we go. Let's do the second one together. And then if you need to go back and change your first one or work on the first one again, you can. Let's do the second one together. So I've got this total accumulation or amount. How do I know that it has to be, how do I know that that can't be net accumulation?
It doesn't start at 0.
Yeah, so it doesn't start at 0, right? So because we've got, at 0, we've got some amounts that's already accumulated, and now we're going to accumulate more changes to it. And so I want to draw a, what did it say H was going to be? 0.2, okay? So our interval is going to be 0.2. So every 0.2. And then I want to come up with an approximate accumulation function, meaning a function made up of constant rates that's trying to be like that one. It's trying to be like this one. And so you guys did really, really well on Thursday knowing that it shouldn't be this. But then for some reason, spring break maybe, lots of you went back to this. Because when I asked you Thursday before break, should it be that? Most of you said, no, it shouldn't be that, right? Why not? Because this is accumulation. And if you have a flat line accumulation, your accumulation isn't changing, then what's the rate? All those rates of change are 0. This is accumulation graph. This isn't the rate of change graph. So if accumulation is not changing, then your rate is 0. But this doesn't work. This isn't a good, I suppose it's a way to approximate the accumulation, but if we want rate of change, it's not going to help us get rate of change because we're just going to get 0 everywhere. So what did we do instead? We said, right, we said that if we want to approximate in that first interval, we want to approximate this curve with a constant rate of change, what will it look like? Straight line, right? Straight lines on linear functions when they're in accumulation give us constant rate of change. So this is a changing rate, so we want to create a graph that's trying to be like this pink one, but is made up of constant rates. So we want this. Straight line. Then straight line. It ends up just being right on top. I was trying to show it. Okay, and then so all of these, we want straight lines. Something like that. So what? This is trying to be like the total accumulation function, but made up of constant rates of change, right? That was our key, because now we can actually build a rate function. So what about this first constant rate? What can you say about it? Is it positive or negative?
Negative.
It's a negative rate of change, right? Because for a change in x, you get a negative change in y. And what about, is it a low negative or high negative? Right, so it's, for a change in x, you're getting the greatest decrease in y of any of it. All right, so then in the first two, we're going to have some constant rate that is, there's no scale on here, so there's really no calculations. And it's going to be, this is rate of change now, so that's a constant rate of change on a rate of change graph is a horizontal line, right? And so then what happens in the next interval? Rate of change is positive or negative, and less or more positive than this one. Or sorry, negative. Less or more negative? Less negative, right? Less negative. So in the next intervals, who knows where, but something like this. Next interval. So all the intervals are a little less negative than the ones before, right? But always negative, right? So in this particular graph, it's still a decreasing graph, or it has a negative rate of change all the way through the part of the domain that we can see. So each one's a little bit less negative than the previous one. So approximate accumulation is straight lines trying to be like the curve, right? And then approximate rates, so those lines have constant rates. So in a rate of change graph, constant rates are horizontal lines, right? Not the value of the dependent variable doesn't change, constant. And those rates, each rate is negative, and they get less negative as you go. So that's what that graph will look like. And so then the approximate or the exact rate of change function is going to look something like this for that accumulation function. So that's what the instructions had you doing. 3 things: approximate accumulation, from approximate accumulation, approximate rate. This is what you filled out at the top of the page, right? And then from approximate rate, exact rate. But we're just eyeballing it and getting the feel for it. Any questions on that? So if you want to later on, if you want to go back and redo number 1, if this wasn't what you did, then that's good practice. Okay, so now we want to start symbolizing these things, start modeling this stuff. Modeling this stuff so we get some actual functions involved here. So let's go on page 2. So now you're going to use h of 0.4. And I want to first start by sketching the approximate accumulation function using h or delta x of 0.4. And we all should nail this now, right? We all should nail this. Using h of 0.4, sketch the approximate accumulation function. Okay, so I put a dynamic version of what you just sketched up on so you can check your work. So this is showing that function you just sketched being generated, an approximate accumulation function. Does it agree with what you did? So our next goal is to write the function for what you just sketched, or what's kind of generated here in pink, right? So what is this? This is a piecewise linear function. Piecewise linear function. Do you remember the general structure for that? Do you remember the general structure for it? We've done it many times. Can you remember the general structure? And so basically you think about this as you're in any interval. So this, what I'm showing right here, consider this to be any interval. Sorry, right here. And writing that function, do we call it g on the sheet? I think it's called g. So this is the point, what? X, comma, g of x. Okay? So expressing the y-coordinate at that point is the same as writing the function. Expressing the y-coordinate at that point, which is g of x, is the same as writing the rule for the function. So how are we going to express the y-coordinate at that point? It's a process we've gone through many, many times before. Can you at least just write down the general structure of what that will look like to write the y-coordinate at that point? In other words, what is g of x? What's the overall structure? If you want all the details, that's fine. We'll get to the details later. But what will the overall structure of that function look like to get the y-coordinate of a point on a piecewise linear function? See, take a minute, see if you can do it. What's the overall structure of that going to look like? Okay, what's the overall structure of this going to be? The overall structure of what we're going to write for the rule to get that y value, g of x. We did it, I think, on the second day of class, and we've been doing it ever since. Is it MDX? Y initial plus? And what is MDX at this point? We're still big picture. No. You're going. No. I don't want detail. I want less detail. Which is the overall structure of this. Y initial plus change in Y. That's what the structure of that's going to look like. There's some Y initial. Y initial refers to what in this picture? Y initial is? So what would Y initial be in this picture? Okay, yeah, so it's going to be the Y value at the start of the current interval, right? So Y initial is going to be the Y value of this point. We're trying to get the Y value of this point. It's going to be the Y value of this point plus the amount of change. How can we express? So we have F, right? We have F, so we've got this point from F. So using F, how do we express the Y value of that point, which is the starting point of our interval? F of, okay, now, but it could be any interval, right? You're right, for what I'm showing you is 0.4, but if it's any interval, what would it be? F of left x, that's what you were saying, good. F of left of x is going to be our Y initial for the current interval. F of left of x. Okay, what's the change in Y going to be? How are we going to get the change in Y? In the broadest sense, first of all. How are we going to calculate the change in Y? Everyone knows it, right? No, I just want the change in Y. Oh, we're using constant rate of change. M dx. M times change in x. Change in Y is M times the change in x. Okay, so M is what? That's the constant rate for the current interval, and that's a function that we built at the end of class Thursday. So for now, we're just going to write that as R of x, and we'll come to define that later. So you did that. You did that at the end of class Thursday before break. You came up with what that R of x was. Why? It's changing, right? In every interval, we get a different rate. Okay, what's the change in x? So we know the rate times the change in x, which is?
X minus left x.
Right, so it's going to be our current value of x from here to here, which is x minus left of x. Some of you are saying, good. So we just wrote g. So we just wrote the y-coordinate of that point that I have there, isolated. But by doing that, we just wrote the whole function g, given f, right? Given f, given our exact rate of change. Sorry, exact accumulation, f. We've wrote a formula for g, or a function for g, which is this approximate, this piecewise approximate accumulation function. And that gets all the pieces because of left of x, right? The beauty of this is left of x always gives us the correct x, the left side of the current interval. So then this generates the whole function. This generates the whole function for all intervals. Okay, does that make sense? Any questions on that? Was part B. So now you're going to sketch on the left corner. If I sketch R, approximate rate function. So you're going to sketch R and then write the definition for R. So and then see if you can do it without looking at your notes. You're going to sketch R over here, and then write the definition for R. What is R? The approximate rate function. It's all these constant rates that the accumulation function, the approximate accumulation function goes through. Okay, check your approximate rate function. It's still an approximate rate. Approximate rate. That's not an exact rate at all. So how do we get those numbers exactly? How would we get this exact value of this rate of change? What would we do? So this is our first interval of 0.4. So we're going to calculate what to get that number? So something like 9 point something, right?
About 9.5.
And how do we get that? Yeah, so that's for this first interval. We got to calculate the rate of change. Is calculated by change in change in y over change in x. So the change in y is going to be what? F of 0.4 minus f of 0 over change in x, which is just 0.4. And so for you'll have to eyeball that f of 0.4. I didn't give you a function, right? No. So you'd have to eyeball. What is that about? 3.8?
Yeah.
So 3.8 divided by 0.4?
9.5.
9.5?
Approximately.
So is that a little bit higher? Okay, yeah. So 9.5, and that's about what it is over there. So now, if we're going to come up with this approximate rate function, we've got to do this in any interval. So again, let me pause it. I'm going to pause life back here. How do we come up with an expression for that constant rate in any interval? It's going to follow this. It's going to follow this pattern, but it has to work for any interval that you're in, not just this is the first interval. Any interval, right? So how can we write that same? And once we do that, that will be what R1 is. This R1 of x will be this whole function, all the steps, right? If we can write a general expression like this that works for every interval, then that will be the rate function. That will be the step function. Can you do it? So that we've done this before, actually. Can you do it without looking at your notes? So rather than f of 0.4, what do we need? F of any starting x value of the interval. Right. Right. So for any interval, the starting x value is left x. No, but actually that's that was the end. Sorry, that's the end of the interval. What's the end of the interval going to be? F of left x plus h, right? So we got to go across. So it's going to be whatever the starting x value of the interval is plus h gets us to the end of the interval. And that's what that first one is. Minus f of left of x. That's what we had all over h, change in x. Okay, so this is our constant approximate rate function. And this is what belongs, this is this R function that we just said we'd table for later in the accumulation function. That goes right there. Okay, so let's talk about finishing the deal here. So what do we got? Everyone good on the approximate rate function and accumulation function? Does it make sense? Any questions? Okay, so let's look at the whole journey here. So we've got, what am I showing here? I'm showing exact accumulation, that's the black one. And then the pink one is approximate accumulation, and from that we get the constant rates, right? Constant rates of change, which are the blue ones over here, the blue steps. are the same the rates of change from the approximate accumulation function. And there's that, what we said, right? There's definition of that. So now what do we want? We want exact rate of change. What's the key to moving towards exact rate of change now? Smaller intervals. So I'm going to make the intervals smaller. Watch what happens. So when I make h smaller, look at what happens to the accumulation, approximate accumulation, and approximate rate. So what happened to the approximate accumulation? Better, right? So now it's doing a really good job of mimicking the original accumulation function. And we've got shorter steps. If I keep making h smaller, now it's almost, the accumulation is almost the same. And what? So now some kind of pattern is forming on our approximate rate. So if I keep making it smaller, we can imagine those h's being so small that we get a smooth curve, right? Here's h of 0.005. The approximate accumulation is virtually the same as the exact accumulation. We can't see any daylight between those. And then when you kind of squint your eyes, it looks just like a curve. But those are actually all just really narrow constant rates, right? Really narrow horizontal little segments, okay? And so then with a very, very small h, just like we saw before, we get the exact rate of change function, exact rate of change function. Okay, so what is that, right? So how do we, when h gets really small, how do we get from there to there? What we want a expression, right? We want an expression for that rate of change when h is very, very small. Okay. Well, it turns out that this approach to that, it's a very good start, but we kind of need to enhance what we're doing over here with the accumulation to make this final step. So to get the exact rate function from the approximate rate function, we need to kind of start over with an enhanced version of this. Okay? Enhanced versions. Let me show you that. All right, here we go. So, only works if h is 0.4. Here we go. Okay. So this is the version we had before, right? So here's what we're going to transition to. This is going to be an improved, new and improved. Ready? Maybe. Yeah. So the new and improved version is going to have to do with the blue sliding interval of h rather than the kind of the piecemeal version of h that we had before. So before we set delta x or h at 0.4, and then we knew where all the intervals were going to be, right? But now let's let that interval always have a starting value of the current value of x. So then as x increases, then that interval kind of slides. And so then when x is at the start of an interval, they match up. But then through the interval, now we've got something different. Okay, so this is going to be the new and improved version. Okay, so will the resulting rates of change be constant rates of change, or that change abruptly, like we saw before, or something else? So for any given value of x, we're going to model the constant rate with what's called a secant line. A secant line. So for any value of x now, the interval is going to start at x, no matter what x is. And that's going to give us, before we had these segments, now we're going to have this secant line for the current value of x that starts at the current value of x. There. So the resulting rate function, is it going to be constant rates that change abruptly or something else? That's the first question on your sheet. Will the resulting rates of change be constant rates that change abruptly like we saw previously, or something else? What do you think? Okay, so if they're so then is that a constant rate?
I guess they would only be constant at a single point.
That's right. Right, exactly. As soon as x changes a little bit, we're going to get a different rate, right? As soon as x increases a little bit, we get a different rate. Because that secant line, the rate for that secant line is continually changing. So our rate function then, it's going to look like this. So the question is this exact rate of change or approximate rate of change? So what am I showing now? The y values of that graph over there are the rate of change associated with that blue secant line for any value of x. Okay? The y values on that graph are the rate of change associated with that blue secant line for all values of x. Is that graph over there approximate rate of change or exact rate of change?
Exact.
So let's pause it here and let's analyze that. So right here, 0.18. Okay, right there. So I'm going to zoom in right here. So the blue line, what is the rate of change that's reflected by the y value over there. The black quote line is a little piece of our curve. So when we find the rate of change of that, rate of change associated with that line, is it going to be the same as the rate of change associated with the curve at that moment?
No.
More or less. So is the approximate going to be too small or too great? Too small, right? The change in y for this blue line is going to be a smaller change in y than what actually is occurring for the same change in x. So where's the actual rate of change function going to be? Lower or higher?
Higher.
Higher. Supposed to be showing it now. So the blue graph is showing what the rate of change associated with that secant line, which is our approximate rate. The actual rate of change is higher because the curve is always steeper than that blue line for any given value of x that I just showed you when I zoomed in. So the exact rate of change is the red one. The blue one's still approximate, but now it's not the abrupt steps. It's continuous also. To be continued. Quiz on Thursday.